Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is efficiency. We're going to look at this final topic in this unit, which relates to machines that we use to do work for us. So in our lives, of course, as you know, we use quite a number of different machines to make our lives easier, to accomplish tasks, and we often have to input energy to get these machines working. Question is, of all the energy we put in, what percentage of it actually comes out the other end as what we call useful work? Well, that is, in a nutshell, the concept of efficiency. So in a moment, I'd like you to pause the video and have a look at the specific questions we will answer, as well as where we are in the unit schedule, and also what the learning goals and success criteria are. And just a little note here, in my last video, I did talk about the concept of kilowatt hours. That was in the power video. So this learning goal, talking about the use of the unit called kilowatt hours and these success criteria, really are not in this video. I've left that for what I did in the previous video, and now that I see, I should also just highlight in here this part right there. We're going to leave that also corresponds to the previous video. Other than that, however, everything you see in here will be discussed. So pause the video, have a look, and then rejoin us. Okay, you're back and we're going to get started here. So first slide, let's talk about efficiency. As I mentioned earlier, when you have a machine or a device whose goal it is to do work for us, we have to input energy, right? For example, you have to put fuel in your car to get you to go from one place to another. Even if you're bicycling, you have to put fuel in you. You've got to eat food, and you have to exert force when you pedal. Same goes for walking. Maybe you turn on a light. This means we have to generate electricity in order to get the light out the other end. Well, efficiency basically answers the question, for every amount that we put in, for every single joule, let's call that the input energy, how much, not output, but how much useful output energy do we get? Now, the reason I say useful output is this. If you think of, let's say, a classic example, the light bulb, especially an incandescent light bulb. So that's the kind of light bulb that you screw into a socket, looks kind of like this. We turn it on, and voila, we have light. We are inputting what kind of energy? Well, of course, it's electrical. However, what are we getting out? Well, of course, we're getting light. If we didn't, it would be a pretty useless device. But we also get a lot of heat. And if you've ever tried to change a light bulb that just burned out, you know what I'm talking about. Heat output. Now, question, which of these two forms of energy is useful? Because in efficiency, we're interested in the useful output. Well, obviously, the light output is useful. The heat output is really just an unwanted byproduct of this device. So suppose I put in 100 joules of electrical energy, which of course I'm going to have to pay for from the power company. How much am I going to get out? Well, suppose I get, I don't know, let's say 2 joules of energy. Now, if I get 2 joules of energy out, then the law of conservation of energy tells me that there's got to be 98 joules of energy that transformed into some other form. What was that form? Well, believe it or not, and I'm not making this up, the 98 joules is actually the useless heat. Believe it or not, these incandescent light bulbs only give you about 2 out of every 100 joules of input energy as useful output energy. And so what can we say about this? Well, if we take the 2 joules that we actually want to use and divide it by the 100 joules input, and we multiply by 100, we get the unhappy number of 2%. And this is what we call the efficiency of this machine that is called a light bulb, that is designed to light our homes. Obviously, it's going to take a lot of input energy to get the useful output energy you want. That's reflected in this low efficiency number. The wasted heat, once again, if there's no other way that we can make use of this, then it really truly is a waste, and therefore it reflects the low efficiency. So what's the formula here? The efficiency is equal to, sorry about the writing there, efficiency equal to the useful output. Sorry, I'm just going to make things fit a little bit better here. Let's do that. There we go. It's equal to the useful output energy divided by the total input energy, and we got to multiply by 100. And then we get a percentage over here. All right? Let's have a look at some examples in real life. I'm just going to put this in a little square here so you'll remember it. This, by the way, is the fact of the video. I guess I should point that out too. You'll have to memorize this formula. It's not a formula that's strictly for physics. It's kind of applicable to any situation if you think about it. But anyway, let's have a look at some examples of common machines that we see or encounter on a daily basis and what are their efficiencies. This table comes from your textbook, which is Physics 11 by Addison Wesley. I'll just expand this a little bit, make it easier, I hope, for you to read. All right, so an electric heater. So this is the kind of heater that you plug in. Let's say you live in your basement, the basement of your parents' home, and it's a little cold down there. So you plug in this little heater, and its sole purpose is to heat up an element, which is actually quite similar to the filament inside a light bulb, and then maybe it has a fan which blows air over that hot filament and therefore heats your room. Here is the efficiency. They tell us 99%, which sounds great. You're actually inputting 100 joules of energy, and the useful stuff, which of course is the heat, is 99 joules. Can you think of why an electric heater is so efficient, but a light bulb is not? Well, for the same reason that the light bulb produces mainly heat, but not a lot of light, the reverse in terms of efficiency is going to happen with the electric heater. Since it is basically the same device, uses a hot filament that electric current is passing through, produces heat, it's really, in a way, a light bulb that's actually producing heat. Think of it as a heat bulb. Of course, there's a fan in here. The fan requires kinetic energy. It's got to blow room air over top of the filament. Now, the kinetic energy of the fan, of course, doesn't really help me. It does blow air around, but it doesn't, it's not like the actual spinning of the blade is what warms me up. So some of the energy that came in is used for other purposes than heating me directly. The fan will make some noise, and that is energy that is not going to heat me. So there is a little bit of a loss, but overall a very well done job, 99% efficient. Let's go down the list here and look at some interesting ones. How about a diesel engine, like in your car or in a truck, for example, or just a regular gasoline car engine? Look at these numbers. These are truly pitiful. What a disaster. If you think getting around in a truck or a car or a van or a bus is efficient, you are absolutely wrong. For every 100 joules of chemical potential energy in the gasoline that we burn in even a diesel engine, such as you might find on a bus or a truck, we only get 36 joules of useful energy out. Now, what is the useful energy in a car? Of course, it's the kinetic energy to move you around, and it's also any other forms of energy, like you might want to turn on the lights in your car. You're going to have to get that energy from somewhere. It might be the winter, and you will need to turn on the heater. Maybe it's the summer, and you want to turn on the air conditioner. Maybe you have I don't know, maybe you have a display that's showing you a map of where you're going, or a screen so that people can watch movies, your passengers, any other device there uses energy. Some of that I guess you could call useful, but most of the energy is lost. Somehow, if 36 joules of energy comes out, then an amount equal to 64 joules will be lost. The question is, where is that going? I'd like you to pause the video right now, take a moment, and then come back, and we will answer that together. Okay, folks, and you're back, and what have we got here? So hopefully you got some time to think about where that extra energy goes. The answer is, not surprisingly perhaps, that this lost energy is in the form of heat. The engine of a car gets very, very hot, a lot of noise is made as well, and all of that is going to mean that you don't have all that energy available to move the car forward, to do what you want. And cars are so bad at this that they're actually only in the 30% range in terms of efficiency. Here's a little more depressing news. The incandescent light that we talked about, 2%. This is why people tell you, replace your incandescent bulbs with fluorescent bulbs. They are more efficient. They're much cooler if you touch them when they're operating, which means they're producing less heat. Problem with fluorescents is they also contain mercury, which can be harmful to the environment. They're also quite fragile. They're a little more expensive, although that's changing. And another thing is some people don't like the quality of the light from a fluorescent lamp. Fortunately now there's a new kind of lighting called LED, which is a lot more efficient. Look for these in your local hardware store. Of course, LEDs, I decided finally a little while back to replace one of these with an LED. These things are under $1 each if you buy in bulk. The LED light, I kid you not, to replace this was actually $30 plus tax. They're extremely expensive right now, although hopefully the price will come down. Mind you, they do say that an LED will save you a lot in energy costs. That is true. It looks a lot nicer than the fluorescents. That is true. And LEDs last a really, really long time. So I place this one in the time that many of these will burn out. So you can actually save money, and they tell you that you will come out ahead in the long run with LEDs. All right, continuing on. Let's try one quick example here that deals with efficiency to the concept of work and energy. So this is a question that is out of your textbook. The textbook is Physics 11 by Addison Wesley, and this is in section 5.2. So what they ask you to do is to consider this pulley system. If you've been in my class, we've looked at pulleys before, and the neat thing about a pulley that is rigged up like this is if you pull down on one side, it will pull something up on the other side. Surprisingly, or maybe not surprisingly, you can pull relatively lightly. Do a little bit of light pulling here, and you can lift something that's very heavy. In other words, a pulley is a machine that converts a little bit of force into a lot of force. Of course, there has to be a trade-off. You can't just convert force infinitely into more and more force. The trade-off, as we've learned in my class on previous days, is that the distance you pull on this side is much greater than the distance you lift. So you get a light amount of pulling, but you got to do more of it to lift something really heavy just a short distance. Anyway, here's how this pulley works. It lifts a 2 kilogram mass a distance of 10 centimeters. So this is what we call the useful work, because this is what we're trying to accomplish. Work, of course, is equal to F cos theta delta D. I'm exerting a force up, as shown here, and the delta D, of course, is also in the upward direction. So the angle between the two is 0. So what I'm going to do is put in here a force upward, which of course, since I'm lifting against gravity, that's going to be mg. Cosine of 0 is equal to 1, so that term I'm going to leave out. And the delta D, of course, is like a delta H. Do you recognize this formula? Of course, it's delta Eg. It shouldn't be a surprise. mg delta H here comes out to 2 kilograms times 9.8 newtons of force on each of those kilograms times the 0.1 meter that it is lifted. And so I get useful work of 2 times 9.8 times 0.1 equals 1.96 newtons. The question is, what did I have to put in to get this to happen? And the answer is found in the problem here. How do we do this? It says we're lifting a 2 kilogram mass. The lower pulley is raised vertical distance of 10 centimeters. This is done by exerting a force of 11 newtons. This is what I pulled with through a distance of 20 centimeters. So the input work, of course, I pulled in this direction. That was the force. And I moved the pulley, or the string rather, in that direction. So once again, I have a cosine of 0 degrees. And so when I go through my F cos theta delta D once again, what are you going to find out? It's 11 newtons, cosine of 0 times delta D, 0.2 meters. 0.2 times 11 is, of course, 2.2. And so now the question becomes, if I realize I made a little mistake here. That's not newtons, that's work, that's joules, and this is joules as well. So if I had to input 2.2 joules of work to get out a useful output of 1.96, what is my efficiency? Well, it's going to be the useful output divided by the total input, and then we're going to have to multiply by 100. And that's going to get me 1.96 joules divided by 2.2. You can see these are in the same units, so those are going to cancel. Then I'm going to multiply by 100. Joules cancels. What do I get when I do 1.96 divided by 2.2? I get 0.89, multiply by 100, get 89%. Not bad. 89% efficiency to make my life easier, and a law of conservation of energy trade-off here, that if I want to exert a light force in order to get a large force out, that's fine. You just have to do it over a greater distance and settle for less distance in return. All right, let's move on. Check. Okay, so let's have a look at another example that uses the concept of efficiency. This one deals with something we've already looked at in this course, the hydroelectric dam or power generating station. If you recall from a previous video on the law of conservation of energy, the idea is to take water that is held behind a dam in a reservoir and allow it to flow down from a higher height down to a lower height, spinning a turbine, which spins a generator, which produces electricity, and that can be distributed to consumers. Now, since we have here a delta H, which I'll try to show you, let's see, seems like the water starts out maybe somewhere along here, and down here is where the turbine is. So we have a fall called delta H. You could call this H initial. This could be called H final down here. The difference is called delta H. And of course, the transformation going on here is that Eg at the top is ultimately being converted into Ek at the bottom. Where does this come from? It comes from the law of conservation of energy, which tells us that the total energy at all points is the same. E total initial equals E total final. The forms of energy are Eg plus Ek. The water could be moving, and that is equal to Eg final plus Ek final. Now we can make some assumptions here. First of all, we can assume at the beginning that the water has no kinetic energy. In other words, it's just kind of sitting there in a lake, barely moving or not moving at all. We can also set the final height to 0. Remember, we are free to set the 0 point for Eg anywhere we want in the problem. Usually we do that at the bottom point. So Eg final ends up as 0. And that leaves us with Eg initial, which I called Ek at the top, is being converted to Ek final, which I called Ek at the bottom. Now, let's look at the question. How much electrical power can be generated by each ton? I hope you know what a ton is. A ton is 1,000 kilograms. By each ton of water that flows through a gate 100 meters, so they're telling you that the initial height is 100 meters above the final height, 100 meters above a water-powered turbine, and they say every second. Okay? They also tell you to assume that the efficiency is 85%, and if we look back on this data table here, it looks like a hydroelectric generator. Here it says 95%. I guess these are just approximate numbers. It could vary from one station to another, so they say in this question 85. That's fine. So let's look at the energy transformation that's occurring in the beginning. We've got EG converting to EK, so let's calculate that. EG, of course, is mgh at the initial point or at the top, and that's going to equal 1/2 mv squared at the final height. And if we sub in the numbers here, we will have 1,000 kilograms of water at 9.8 newtons for each of those kilograms, falling 100 meters. Let's just calculate this number for a moment, and you'll see why in a second. 1,000 times 9.8 times 100 equals 980,000. So that's how many joules of potential energy. Now, I know some of you are looking back here and saying, hey, why didn't you cancel the masses and just solve for the speed of the water when it comes out at the bottom? The answer is, I'm not interested in the speed of the water in this question. The question doesn't ask me about that. What the question is actually asking is the following. If you take all of that energy and you convert it to E kinetic, which is going to spin the turbine and generate electricity, well, if all of that kinetic energy and gravitational energy could become electrical, then we would get 980,000 joules of electrical energy. However, because the power plant is not 100% efficient, therefore, we don't get all of that. In fact, how much do we get? We get 85%. So we have to multiply this number by 0.85, which is the decimal way of saying 85%, in order to get the electrical energy produced. And I'll show you what that comes out to. 0.85 times 980,000 joules. So here we go, my calculator times 0.85. I get 833,000 joules of useful electrical energy, which means just over 100,000, around 150,000 joules was lost. How could you have done this using the formula with efficiency? Well, remember, we have efficiency as a percentage is equal to the useful output divided by the total input times 100. So what you could have done here was put in the number 85 for the percentage is equal to X, let's call it, divided by the total input. That was the total available energy in the beginning. And if you solve for X here, you're going to see that you get the same value down there. Of course, don't forget to sig fig this correctly. I think we're looking at 2 sig figs, 3 sig figs. Here it's hard to tell how many sig figs they mean by a ton, so let's call it 2 sig figs, 8.3 by 10 to the 5 joules. All right, so there's an example using the law of conservation of energy and efficiency. We're going to finish up with one final example, this one also dealing with the production of electricity, this time from solar cells. I'm sure you can all recognize what's going on here. We have a bunch of solar cells spread out. This picture is an image out of Google Images. So was the other one, by the way, with the hydroelectric dam. And these are situated in the desert where the sun shines pretty much all the time. And because you're near the equator, the directness of the sunlight is a pretty high number. So you get very intense sunlight many days of the year. Why not convert some of that light energy from the sun into electrical energy? That sounds like a pretty good proposition. After all, light energy from the sun is free. Why not convert it into something useful that we need for our daily lives? Of course, you're not going to get all electrical energy. What do you think is going to happen to these solar panels as they sit out in the sun? Pause the video for a moment and see if you can think of it and then come back. All right, did you figure out? Of course, they are going to get very hot. So there will be some heat energy in there as well, which means that for every 100 joules of light energy input, how much am I going to get out? Well, let's read the question to find out. It says, if you read through the question, that the cells are 20% efficient, which means that for whatever reason, you're going to get 20 joules of electrical plus, I guess I could put heat and other, because I'm actually not an expert on solar panels, so there may be other forms of energy involved that I'm not aware of, but whatever the case may be, 80 joules of energy does not become electrical, therefore the efficiency is 20%. Now let's read the question to see exactly what they're asking. They say the solar cells occupy an area of 50 square meters. Okay, we know what that means, we know what area is, and it receives 150 watts of energy, of power rather, per square meter from the sun. Now, what does that mean? Well, think for a moment. The sun shines down on Earth, and I'll try to draw this for you as best I can. I was never known for my art. That's why I didn't become an artist. I became a physics teacher, right? Here's the Earth, let's say. Make it blue. And here's the sun. I would make the sun yellow, but you'll have trouble seeing that, so maybe I'll make it orange. And let's put the sun. Of course, the sun is much bigger than Earth, but because the sun is so far away, it looks small. Anyway, my point is as follows. The sunlight that hits the Earth, you could imagine it as doing something like the following. Let's imagine that the rays of sunlight kind of spread out as they travel toward us as follows. However much power, however much energy per second comes to us from the sun, the point is that it hits the Earth and it is spread out over the land and the sea, of course. Now this is a two-dimensional drawing that I've made for you, but if you imagine a flashlight and a globe, you'll get the idea. The light energy spreads over the surface of Earth, and of course, whenever we talk about a surface, we're talking about area, which means we're talking about square meters. Now, the amount of power coming from the sun, you can calculate this, you can look it up if you want. You can actually take the total power, you can figure out how much of that is coming in our direction, because remember, some of it goes off the other way into space and doesn't reach Earth. We're not interested in that. There's a calculation you can do to figure out of all the sun's power, how much comes our way, what is the surface area that it hits on the Earth, and you can do a calculation that involves the total power hitting the Earth divided by the surface area. So you're going to get power, we know, is watts, area is square meters, and the number they're telling you in this problem is 150 watts per square meter. This number is actually a little bit low from what you'll find if you look this up officially. I don't know why they're picking this number. In a desert, I'm pretty sure this number would be higher than what it is in this question. However, let's just go with what they have. They're telling you there's 150 watts per square meter of power. This is called the intensity, how much the power is concentrated in each square meter. And if you're getting 150 watts per square, sorry, not watts squared, but watts per square meter, and that is falling onto solar cells that occupy 50 square meters, look what we can do with our units here. If we multiply these two numbers, we will get watts, which is power. Now 150 times 50 is 7,500. So 7,500 watts of power is what is going to hit in terms of light energy. Unfortunately for us, these solar cells are only 20% efficient. So think of this as the available energy or the input energy. We know that we're dealing with an efficiency of 20%, so let's use the formula. Percent efficiency equals the input, equals the useful output divided by the total input times 100. And so when you put in 20 equals x over 7,500 times 100, what are you going to get? Let me just give myself a little bit more room here. We are going to get x equals, it's going to come to 20 over 100 times 7,500. And that's going to be 7,500 times 0.2 equals 1,500 watts of power. So there you go. How much power do they generate? 1,500 watts, even though there was 7,500 available. I don't know too much about about solar panels, I hate to admit. I do know that they have some very interesting physics in them, which deals with semiconductors, and if you're really interested in this stuff, it is certainly worth looking up. There is a lot of job opportunity and future in solids and semiconductors. Your computer chips, any electronics these days, deal with the same basic physics about what's going on in these solar panels rather. And so if you want to learn more about this, you guys know what to do. Check it out on the internet, start learning, start reading, get ahead of everyone else so that when you do go to university, you'll have a leg up on everyone. Maybe you'll land that engineering job with some Silicon Valley company and get paid the big bucks down the road. That would be great. Anyway, there's your lesson on efficiency. We've looked at it in terms of solar panels. We've looked at it in terms of energy conservation and conversions, such as the kind of question we've been doing up till now. We've even looked at it in a new situation of a pulley and work, and I hope you understand everything, and I will see you in class. Thanks for watching.